Okay, so here we've got another problem that is all to do with an object and a pivot point. Okay, so you've got this object here, slightly funny shape, and it is supported by this pivot point and then this string here that is held by a Newton meter. So it's able to pivot around there, but it's held at the moment stationary. It's able to pivot around here, but it's held stationary. So everything's in equilibrium. And you are told in the question, I removed this from the question just to make the diagram simpler, 1.2 kilograms is the mass of this object. Okay, so it's 1.2 kilograms. That's the mass of the object. So if we know the mass is 1.2, then the weight is 1.2 times 9.81. Okay, so 1.2 times 9.81 is going to give you, 1.2 times 9.81 is going to give you a weight of 11.77. So we can round that to 11.8 newtons. Okay, so that's the weight of this object acting downwards. And what we're trying to work out here is this distance here, this distance d. Now you're also told in the question, and I again remove this, that T is 5.1 newtons. So T is equal to 5.1 newtons. So this is information that's given to us. Right. Now, in this question then, we know that everything is in equilibrium because we know the object is static. So therefore we can use the principle of moments. And we know that the sum of the clockwise moments equals the sum of the anti-clockwise moments. And that is the crux of this matter. So clockwise, we've got the weight acting clockwise, and we've got then the tension acting anti-clockwise. So clockwise, we've got the weight, which is 11.8, multiplied by the perpendicular distance from the pivot point, which is d. And remember, importantly, this distance is the perpendicular distance. Now, in this direction, we've got a problem because we've got the tension here, but we don't know its perpendicular distance, because the perpendicular distance would be that distance there. Well, I'll just call it x, okay? We don't know that distance. That's your perpendicular distance of that force from the pivot point. We don't know it. So we can either work out that distance x, or we can resolve, or we can resolve this force into two components. And we're going to do it that way. So this force here, this tension, can be resolved into two components. The components are, if I change the color of the pen perhaps, might help. The components of this tension are perpendicular to one another. So one component is going to be horizontal to the object. We're not worried about that one. And one component is going to be perpendicular to the object, and that's the one we want. Because once we've got that, we've got the component of tension acting directly upwards, vertically upwards. We know its perpendicular distance then from the pivot point, so that's going to help us. Okay, so how do we work that out? Well, we've got here a right angle triangle. We know the hypotenuse because we know that T is 5.1. We're going to work out the adjacent, and we know this angle here. So this side is adjacent to this 40-degree angle. So to work out this component of T here, it's just going to be 5.1. Well, if you think about it, let's try and explain this a bit better. So if we come down here, we know that this adjacent, cos of 40 is equal to the adjacent over the hypotenuse, which is 5.1. So the adjacent is going to be 5.1 cos of 40. Okay, so that 5.1 cos 40 is this component of tension, which is perpendicular to the, well, I don't want to say perpendicular because this is on a slope, but which is perpendicular to the horizontal. Okay, so 5.1 cos 40 is our force acting vertically upwards. The perpendicular distance of that force from the pivot point is 0.75. So that is our anti-clockwise moment. And therefore D will come out as 5.1 cos 40 times 0.75 divided by 11.8. Okay, so if you work that out, 5.1 cos 40 times 0.75 divided by 11.8, that's going to give us our answer of 0.25. We'll round it to 0.25 meters. Okay, so that's that one.